So welcome to today's tutorial, Introduction to Property-Based Testing. We have two tutorial leaders today. We have Zach Hatfield-Dodds, and we also have Ryan Soklasky. I hope I got that one right. Yes, so just give me 1 second and make sure that I have everything right before we begin. So I want to tell you a little bit about our tutorial hosts for today. So Zach, and I believe there's someone coming in. Zach's modest goal is to help everyone write better code, mostly via bug finding tools. Zach spends his time working on Hypothesis, PyTest, and other open source projects. I love PyTest. Along with Hypofuzz and his PhD at the Australian National University. And if you can't get to him via a computer, Zach can probably be found with a good book, a pile of chocolate, a long walk in the bush, or all three. Maybe Zach can chat with you about some of his favorite book recommendations. And then Ryan is also a Hypothesis core developer. Ryan works at MIT and has been teaching various fashions since his time as a high school tutor or university TA. Ryan runs the CogWorks course for MIT's Beaverworks Summer Institute and wrote python-like-you-mean-it.com. So Zach and Ryan, I'll pass it over to you.
Thanks very much, Laura. Ryan, do you want to say anything before we jump into it?
Not much other than I'm really excited. I think that Zach and I have a really cool tutorial for you all, and I hope you're ready to learn some neat properties to test.
Cool. All right, then. So let me share my screen, and we will be able to see our talk. Let's get Zoom sorted out. All right, so this talk is informatively, but perhaps unimaginatively titled An Introduction to Property-Based Testing. As we said in the tutorial description, we do expect that you've probably done some testing before. So you might be familiar with unit test or hopefully with PyTest, which is what we'll be mostly using today. But we don't assume that you have any familiarity whatsoever with Hypothesis, which is the library for property-based testing we're talking through. And here's our plan for the next 3 hours or so. We've basically gone through the welcome and the introductions, and then we're going to have sort of 4 chunks of the tutorial. For each chunk, Ryan and I will give a short talk, and then we're going to hand it over to you guys to work through some exercises that we've written to try to bed down the things we're telling you and let you apply them hands-on in case you learn better through your fingers than through your ears. Halfway through, we've got 10 minutes set aside for break time for chocolate, if you like chocolate, or coffee, if you like coffee, or just standing up and having a stretch. So let's jump into the first bit where we explain what exactly is property-based testing. Oh, if you have any questions, please feel free to drop them in the chat. And Ryan can answer some there, or he can pass some on to me to drop into the presentation as well. So property-based testing 101. Kind of begs the question of what is testing anyway? And I won't pretend that there's a single correct definition, but the one that we're using for this tutorial is that testing is the art and science of running your code and then checking that it did the right thing. There are lots of other ways to help you write code which does the right thing or detect when your code is doing the wrong thing. You might put assertions in your code. You might use a type checker like MyPy, a linter like PyLint or Flake8. You might get a friend or a colleague to review your code or do the same for them. Or of course, you might get enough sleep or potentially just drink a lot more coffee. All of these things are great, but they're not testing, so they're not what I'm talking about today. There are also a number of different kinds of tests that you might have heard people talking about. The boundary between unit tests and integration tests is always kind of fuzzy. But you also have things like snapshot tests, where you might record the state of your web front end and check after each pull request that the screenshot is the same. You might have parameterized tests, where you write a table of inputs to a unit test. We'll see one of those in a moment. You might have fuzz tests, and of course, we're going to tell you a lot about property-based tests. Stateful model-based property tests are a cool topic that we will not be covering. They're just here for completeness. So let's imagine that for some reason we no longer trust Python's sorted function. So we want to test it. We might want to test that it works for lists of integers and for floating point numbers and for strings as well. We should be able to sort things which we can compare even if they're not numbers. And so hopefully these tests all make sense, right? We sort 1, 2, 3. We expect to get 1, 2, 3 back. If we sort the list of floating point numbers 3, 2, 1, then we expect 1, 2, 3 as floats to match the input. And if we sort the letters B, C, and A, we should get the letters A, B, and C. Okay, so far so good. If we want to take the sort of don't repeat ourselves mantra, we can put this in a parameterized test. This is maybe a little more boilerplate to start with, but it ends up making it much easier to add further tests. So if we think of more cases, we can just add them to this list rather than copy pasting the whole test function. In particular, if you copy paste the test function and forget to update the function name, then you don't in fact have more tests. You have the same number of tests and less tests than you thought you had. So if in doubt, parameterized is a really neat trick. But for a parameterized test like this, we still have to know in advance what the correct answer is. And okay, for lists of 3 elements, this is pretty easy to get right. But for more complicated code or for much longer input lists, we might want to try to write a test where we don't have to know the correct answer in advance. And so one option is just to pass the arguments and then to use some other way to work out what the correct answer should be. And in this example, maybe we don't trust the sorted function anymore, but we do have a trusted sort function that we can compare it to. So we just say that, like, given whatever list we have, when we sort it, that gives us the same output as if we sort it using our trusted sort function. And this actually comes up quite often in practice. You might not have a totally separate implementation, but maybe you can compare it to the run from before your pull request, or you can compare the single-threaded version to a multi-threaded version, things like that. If you don't even have a known good function to compare to, though, all is not lost. We can still check the results of our function. So in this case, we check that for each pair of elements in our result, that is the 0th element and the first and the second, and so on, then the earlier element is less than or equal to the later element. Does this seem like a good test? A couple of answers in the chat, please. Seems like a good test? Awesome. React emojis are also good. I reckon this is actually a pretty good test. The trouble is, you could also make this test pass just by deleting all but the first element of the array. And that maybe is not so good. So if we don't want to be able to have that thing, it's not enough that the return value is a sorted list. It should also be the same length as our input and have the same set of elements. Do we think this is a good test? Bernat, was that the previous one was sad or this is sad?
The previous one.
Yeah. So this is a much better test. And to be honest, I find it hard to think of a bug in a sorting routine that would still pass this test. In order to sneak a bad function past this test, you would have to have it give you an input that has duplicate elements, delete one of the duplicates, and then duplicate a different element instead. For example, going from the list 1, 2, 1 to the list 1, 2, 2. That would still pass this test, but I mean, come on, is that really a realistic bug? Never mind, we will press on anyway and see how we could catch it. So the second property of sorting is actually that our output should be a permutation of the input. That is, it should have the same elements, just in a potentially different order. And as it turns out, the Python standard library can give us the permutations of a list. The only problem with this test is that there are very, very many permutations of long lists. So if you want your test to finish running before the heat death of the universe, you might want to use the collections.counter class instead. So here we are. This test seems pretty good to me. And even better, we've discovered property-based testing. Congratulations, everyone. It turns out that a sorting function is what we call fully specified by just two properties. And fully specified means that if any function satisfies both of these properties, then it's a correct sorting function. So the first one is that whatever our output sequence is, it's in order. It's got to be in order for it to be a sorting function. And the second property is that we have the same elements in the output as we had in the input. And it turns out that this is kind of the definition of sorting. It's taking the same elements and putting them in order. So we're done. What I don't want you to take away from this, though, is the idea that a thing has to be fully specified for property-based testing to be useful. Even this version is pretty useful because it will detect any case where your output elements are not in order. And this one, even though it's like technically possible to sneak a bad function through this test, I think it'll still catch almost all the bugs you have in practice. No testing is perfect or totally foolproof, but they can be fast and still give us much better confidence in our tests. So here we are. Now, this tutorial is going to focus on hypothesis, not just PyTest. And so I'm going to show you how to write exactly this test, but using hypothesis to come up with what these arguments should be. That saves us the trouble of having to think up all the different lists of numbers that we might care about. Here it is. So we have exactly the same test body here. We're leaving that alone because it's a great test body. And what we have is a different decorator. So we say, given that our argument is one of either lists containing a combination of integers and floats, and this could be any list containing integers and floats, or it's a list containing text, which is to say Unicode strings, then run that same test body. Do we think this test will pass? Ryan thinks it will pass. I thought briefly that it would have a problem, but it turns out that the first problem it has is that this can generate empty lists because we haven't specified the minimum size. And our test body assumes that we have at least one element in our list. And so if you actually run this test, you'll probably get an index error, so slap your forehead and add the min size equals 1 argument to these list specifiers. If you do that, though, you'll discover that if we generate not a number returns false from any comparison. And so even if our sorting routine works, our test will complain that outputs aren't in order. It's a great question about what ST is. Thanks, Melinda. This is the hypothesis strategies module. So it contains a number of what we call strategies that help you describe what the possible arguments could be. And so here we're using 4 different strategies. We're using one of to combine strategies. We're using the list strategy, which describes lists, and then integers, floats, and text. Okay, I can't count. That's maybe 5.
Just a note,
okay, Ryan.
Slices slices don't care about bounds. So actually it does.
Of course, yeah.
That does behave well, yeah.
There we are. If I had actually run the test, which you should always actually run your tests, I would have noticed that. Thanks, Ryan. So the summary from this part is that property-based testing is really useful because it means that I don't have to think of all the weird edge cases. I can just describe what the data should be and then have the computer think of the weird edge cases for me. Checking whether or not our results are wrong in particular ways can be useful even if we don't know the right answer for our function. And this means, to be clear, that I wouldn't recommend property-based testing for everything. Depending on the project, I reckon maybe between 10% and 90% of your tests should be property-based. But on any project, you'll still want to have some traditional unit tests where you write down the full expected answer, just to check for some weird edge cases maybe. And property-based testing is unique to me because it can help me find bugs in my understanding of the code, not just finding bugs in the actual code that I wrote. And something that we didn't see here was that we often don't actually need assertions in the test. Often, even just calling your functions or your code with really weird inputs will turn out a lot of bugs. And so putting assertions in your code, not just in your tests, can be really useful for that. And that brings us to the first round of exercises. So the plan now is we're going to split into 2 breakout rooms for about the next 20 minutes. So we'll come back together at, I'm going to say 20 minutes to, or 40 minutes past whatever hour it is in your time zone. Until then, let's go to the testing tutorial repo. If you haven't previously installed the dependencies for the tutorial, you can do that. And then we'll follow the instructions to get some hands-on practice. Do you want to say anything before we jump into that, Ryan?
Yeah, so we'll be tracing through the steps of what Zach just covered. The notebooks are pretty detailed. So if there were any parts that you wanted to kind of see laid out carefully, the notebooks will lay those out for you.
All right, everyone. Welcome back from exercises part 1. So let me share my screen again. And let's get into it. So part 2, or our second chunk of the tutorial, is about describing your data with hypothesis. So we've seen what a standard unit test and a parameterized test and a property-based test look like. But you might be thinking something along the lines of, but my code mostly takes things more complicated than just lists of numbers or strings. The good news is hypothesis can cope with that too. And so that's what this chunk of the tutorial is about. I'm going to give you a quick overview right at the start so we have some context. Hypothesis has a whole pile of different, what we call strategies. So that's the st dot prefix. We usually import hypothesis strategies as st, just so that we have that shorter name. You can generate scalar values like none or booleans or numbers, dates and times, time zones, all that kind of thing. You can generate collections of things, whether it's lists or tuples or dictionaries. We'll get into the details later. You can modify what the strategies produce using what we call the map and filter methods. There are a number of special strategies like the just strategy, which only generates the single value that you pass to it as an argument. And again, a number of other specials that we'll get to in more detail on later slides. There are a couple of different ways to generate recursive data. If you have something like any JSON blob as the value, that could be one of the scalar types or a collection, or it could be nested data in some sense. And then to save time, we have a number of ways for hypothesis to infer what strategy it should use based on something like the type hint or the NumPy element type, or if you're using Django, the fields and the models that you have can be used to automatically generate data. And then we'll wrap up with sort of an overview of where you can find these strategies, and then a few useful exercises, or recipes, sorry. The exercises then will focus mostly on just generating the data, not so much on writing the test body. So let's jump into it. The scalar values, I mentioned none and booleans. Numbers we generate usually have an optional minimum and maximum value argument to the strategy. So you can say things like, give me integers that are at least 5, or give me floating point values between 1 and 10. If you're looking at floating point values or at decimals, you can do things like excluding infinities, even if you don't have other bounds on them. You can generate strings, whether you mean Unicode strings or byte strings, control the code points and various other things. And then we've also got great support for dates, times, date times, and of course, time zones. If you've thought of anything else, hypothesis can probably generate that too, but the slide would start to get cluttered if I went through all of it. Collections, there are basically 3 different ways to generate collections that you'll come across a lot. The most common is going to be things that look a lot like our lists strategy. We have the elements, which is what strategy should we use to generate the elements of this list. We have these optional arguments to control the size of the list, that is the minimum and maximum length. And then we also have the unique by or unique arguments. So if you want a list with no duplicate elements, you can just pass unique equals true. Or if you want a list where, for example, none of the strings start with the same letter, you could pass unique by and a function that will get the first letter of that element. And so this strategy is actually the foundation that we use to build many of our other collection strategies. Things like dictionaries are essentially pairs of elements that we then turn into a dictionary. Sets are just unique elements. Iterables are pretty much lists that we apply the iter function to. The second type of collection that you'll use a lot is the tuples strategy. And the tuples strategy takes a variable number of arguments, and it will generate a tuple of that many elements, each element drawn from the corresponding strategy. So if you want something which is, for example, an integer, a string, and a Boolean, you could use tuples, integers, text, Booleans. And that would always be of length 3, and the corresponding elements would always match up. I think of this as being kind of like the star args thing that you can pass to a function. And then to complete the set, we have the fixed dictionary strategy. For the fixed dictionary strategy, you actually pass that a dictionary of the keys that you want. So you have to know all of the keys in advance to use this, plus the strategy corresponding to each key. You can have optional and required keys, but this is sort of similar to tuples, but more for like star keyword arguments. And I mentioned before that you can kind of apply a thing. And there's two ways that we often transform our strategies using methods on the strategy object. For example, you can use map. So strategies.integers and then map string. This gives you a new strategy which will generate strings. But those strings will be created by first picking an integer, calling string with that value, and then returning the string that we just generated. The other useful method that we have is filter. So if you have a couple of examples that you don't want to see, for example, if you're testing division and any number is fine except for 0, then you can use the filter method, and it takes a function which just returns false if we should try generating a different input instead. And so integers.filter bool or .filter lambda x not equal to 0 would generate any integer except the ones for which that function turned false. We also have this assume function. It basically acts the same way as filter, but you can call it inside your test as well. So that's useful sometimes. The general tip for filter is that if you're rejecting more than about 20% of the possible examples, you'll start to see some slight performance issues just because Hypothesis has to retry things more often. And at that point, I'd start looking for a different way to write my strategy which didn't use filter. Here's an example of using map and a filter. So let's say that we want a tuple of 2 integers where the first integer is not larger than the second integer. So the first option is we could use a filter. We could say, well, for any of our tuples x and y, if the first element is less than or equal to the second element, then that's okay, generate it. Otherwise, we'll try generating something else. And, roughly half of our inputs will pass this test. Alternatively, we could just chain map calls. So we could say, take that tuple of 2 integers and sort it, which will give us a list, and then call tuple on it so we get a tuple again. And this will work for 100% of integers.
Zach, just one clarification. You mentioned it would pass the test. That lambda actually is not testing our code. That is a condition that must be passed for Hypothesis to generate that data.
Yep. Thanks for the clarification. Questions in the chat as usual, if you have any, please. So the next strategies that you'll probably use a lot are the just and the sampled from strategies. And these are a little special. The just one basically takes a value and gives you a strategy. So if you have something like the lists strategy where you have to pass it a strategy, not just a value for the elements, you can use just to basically turn a value into a strategy. But that strategy will only ever generate the value you gave it. So if the only time zone you want to deal with is UTC, then just UTC for your time zones. If you've got multiple possibilities, then sampled from is the thing you're after. And this is pretty straightforward. How do we join our database? Well, it can be either an inner join or an outer join. And a Hypothesis will just pick one of those options for you each time you run the test, each time it executes the test function. Sampled from also works really well with the nums. including if you've got flag enums where you can combine various fields. So if you sample from like read, write, and execute permissions, you'll get each of the permissions alone plus all the various combinations. Another set of useful sort of special strategies are the one of and the nothing strategies. One of, we actually saw this way back with our first example. One of just combines two strategies. It basically says either give me an example from this one or from that one. And okay, it can combine more than two at a time as well. So if you want, for example, none or a Boolean or an integer or a string, you could have one of, none, Booleans, integers, strings. And the nothing strategy is a neat little complement to this. The nothing strategy just vanishes when you call it with one of, because it can't generate anything. So this often makes a nicer default value than sort of a strategy or none, where you have to have the like, if X is none, then do something else logic. Often you can just pass the nothing strategy and it will combine in the way that you'd hope to. We can add strategies together using one of, but unfortunately, it's not generally possible to sort of subtract strategies or work out how to generate something that could be generated by either of two strategies. And that's because if you've used map or filter, for example, with your own custom function, it's not really practical for us to work out how we would generate a thing that passes through that function. All right, another favorite special strategy. If you've got your own custom classes, you probably don't just want integers, you actually want like an instance of my class. And the build strategy will give that to you. You pass the build strategy, the thing you want to build, strategies as positional arguments corresponding to the positional arguments of the thing, and strategies as keyword arguments for the keyword arguments of the thing. And this little bit down the bottom is basically how it works. I'll walk you through it quickly. So we have the thing to build and the arguments of the keyword arguments. We'll generate a tuple consisting of tuples of positional arguments plus the fixed dictionaries of keyword arguments. And then we'll use map to actually construct an example of our thing using the args and the keyword args that we just created. This is, I know, like a lot of Python syntax on a small slide. So let's just skip on to recursive. If you have data like JSON, for example, or other things where you have like a tree structure or a recursive structure, just writing a few layers of the tree works pretty well, but you can do better by using the recursive or the deferred strategy. My simple rule of thumb here is that if you're using @composite, which we'll see in a minute, you can just write recursive function calls, and that will be fine. If you're not doing that though, for example, in this one, we can't have self-referential things because JSON isn't defined until afterwards. So we can use recursive to define our base case. And our base case for JSON is these scalar values. JSON can represent null or true or false or a number or a string. And then the collections in JSON can either be lists of any JSON object, or they can be dictionaries of a string key to any JSON object as the value. And so this strategy, which I've assigned to the JSON global, can actually generate any possible valid JSON object. Another way to write this using deferred would be if we really did want to have a self-referential strategy, you can use deferred basically just to put the name error off. I'm not going to show too many examples of that because it doesn't come up very often. But if it does, look up deferred in the docs. Still no questions in the chat. In order to save time and to make it a little easier to work with hypothesis, we also support what I call inferred strategies. And so this is where hypothesis can inspect your code in some way and work out how to call it for you. So if we look at the builds example, here you would have to pass all of the arguments and keyword arguments to builds, even if you've already got type annotations on your code. And so the from type strategy is actually integrated with builds. If there's a required argument to the thing to build, which has a type annotation, but you don't pass a strategy, hypothesis will just look at the type annotation for you and work out what strategy it should use for that argument. Now, this isn't magic, or if it is magic, it's the kind of magic in the real world where some magician has just done a lot of work behind the scenes to make this work. So if it doesn't work for you, you always have the option of just filling in the relevant strategy by hand. Bernat, unfortunately, it doesn't work with stubs or type comments because I can't work out how to do reliable runtime introspection of those things. However, there is a com to an, so a comment to annotations converter written by Lukash, which you can run over your code before to convert away from typed comments. And since it's a time saver, we've also been careful to make sure that using some inferred and some manually specified strategies works well. Of course, if you've gone to the trouble of working out how to construct your object because the automatic inference doesn't work, you can just use the register type strategy function to tell Hypothesis how to do that. And so that's a great thing to put in your setup code for your tests, after which you can just infer your way through pretty much everything else and save a lot of time there. The general pattern of inferring strategies turned out to be pretty useful, so we've applied it in a few other places too. One common one would be the from regex strategy. Thanks, Bernat. So if you have a regular expression, for example, for phone numbers, you can generate matching strings using the from regex strategy. If you want Python variable names, one useful trick is to kind of start with a regular expression that usually gets it right, and then use filter to clean up the remaining cases. And this is a great use of filter. Trying to build a regular expression which matches exactly valid Python variable names or identifiers is a complete pain, but getting close-ish and using filter to clean it up works really well. If you're into NumPy, we've got quite a lot of inference there because NumPy has great support for data types and so on, and for shape signatures. And so whether you're doing basic stuff where you just want to get the right size of float or complicated things with matrix multiplication, we've got you covered there. And if you're using something like Django, we've got from field and from model functions, which will guess the correct strategy to fill out whatever you have in your database or your form. Design tips. If you want to build your own inference functions, which I do find is a useful pattern, it can save time, it can make testing easier, and in particular, you can build things which are specific to your project. A couple of bits of advice. The first is, it's much better in our experience to err on the side of generating too large a variety of things. And that's because having your tests silently fail to detect a problem tends to be a lot more frustrating in the medium to long term than having your tests fail when you didn't want them to because it generated too much stuff. If they fail when you don't want them to, you can customize the strategy. If they don't fail when they should have, it can take a lot longer to work out. And the other tip is that it's really valuable to support a smooth path to kind of gradually specify more or infer less. Otherwise, you can end up in a sort of awkward position where your inferred strategy is no longer quite working for you, but in order to fix that, you have to like rewrite the whole thing from scratch. And that's just not much fun. So coming back to our last set of special strategies, these are for when you really have to define your own thing. And so they're great if you have particular objects or classes in your project. So these are ways to generate data which has kind of complicated internal structure where you don't want to use a filter. For example, if you want to generate a list plus a valid index into the list, generating lists of a random length plus integers randomly will often end up with having integers that are too large to index into the list. On the other hand, we can start by generating a list and then generate an integer between 0 and the length of the list, and that will usually work. In simple cases, you can just use flat map. That's another method kind of like map, but where map returns the value that the strategy will generate, flat map returns a new strategy which we then draw a value from. Honestly, I mostly only use it for this kind of cute recipe. I go from type, that is, generate any type that Hypothesis knows about, then apply from type to get an instance of the type that we generated. So from type, flat map from type is a lovely tongue twister, and it can generate just about everything. On the other hand, for anything that's longer than that, I would tend to use the composite decorator, which will turn any function that you write into a strategy. It's capable of exactly the same things, but the code tends to be more readable. In this example, the way composite works, always, not just in this example, is by supplying a draw argument, which is always the first argument to your function. You can name it other things if you want to, but by convention, we call it draw. And your function can then take whatever other arguments you like. So our custom widgets strategy, for making widgets, of course, will first check that whatever our key is, it's a string, and that it's at least 3 characters long. That's a secure password policy, right? I mean, the empty string would not be a secure password and could cause other bugs too. So what we'll do then is we'll pick a factory, which is drawn from our factory locations, and we'll pick a power supply for our factory, which is between 0 and whatever the maximum voltage for that factory is. And then we'll have the strategy generate a widget, which is made with that amount of power in whatever the location of our factory is, and has the default password that we've set up. All right. There's a useful recipe though, which is you might not want to have this assertion run, especially more expensive assertions run, every time that you generate an example from the strategy. And so this is a recipe that I think of as the inner composite trick. It's great for reusable strategies because you only pay the cost of input validation once, but you still get all the benefits of composite. You just get to pay the input validation once and then only pay for the generating of the actual value each subsequent time. Don't get caught up though. Occasionally I see people using composite where they only call draw once. And in those circumstances, you can probably just return a strategy object from your function. And so this general design pattern of I have a widgets function and it returns a strategy to build widgets. This works pretty well a lot of the time. It's a great pattern for reusable strategies, which you can customize like this. And often it will be just a little bit cheaper than composite. Same reason. You only do the validation once, and then you don't have to pay that cost every time you're generating an example. If you're calling draw twice in a composite strategy, I'd still check briefly whether or not you need composite 3 or more times, and you probably do. Our last really special strategy is data. The data strategy is pretty much like composite, but you can pass it into your test function, not just a function that generates a strategy. This is basically all of the power that you get from the composite decorator, plus everything that you get from awareness of what your test function has done so far. At this point, it is an incredibly powerful tool. You can have arbitrary state and dependencies between the behavior of your code and the inputs that you generate. But the downside is it's so flexible and powerful. In particular, that flexibility means that we have to report each draw separately rather than just showing the inputs to your test. And that can complicate the terminal reporting. Like what example failed is just a more complicated thing to talk about when you're using data. Use it if you need it. It really is powerful and useful. But if composite would work, I would usually recommend using composite instead. All right, last topic for the describing your data section is where to look for all of these strategies. So the first place, of course, is our core strategies. This is the hypothesis.strategies module. These strategies don't have any dependencies outside the standard library. So therefore, standard library and built-in Python types usually. There is an exception. For example, the zone info module for time zones was newly introduced in Python 3.9. So if you're using earlier versions of Python, then you'll need the zone info backport from PyPI to use that strategy. The extra strategies are where we put things that are supported by the Hypothesis core developers, but also have some extra dependencies. For example, for the NumPy strategies, you need to have NumPy installed. And so we store those in hypothesis.extra.numpy. If you want to generate pandas objects, they're in hypothesis.extra.pandas, and you might have guessed you'll need to have pandas installed. Similarly for Django or for dateutil time zones. Bernat asks, how do I pick time zone implementations between dateutil and zoneinfo? Hypothesis doesn't make that choice for you. If the question is, how would I choose between them as an application developer? I would always use zoneinfo now, since it's in the standard library and follows the standard interface. On the other hand, dateutil follows the same interface and is quite compatible. So if I was already using that, I'd just stick with it. I haven't mentioned here, but Hypothesis also supports generating PyTZ time zones. PyTZ is notable because it actually predates the time zone standards for Python a little bit. So if I'm starting a new project, I'd probably avoid it, but it is widely used, and so we do support it still. And the final point, of course, is that the Hypothesis core devs haven't thought of literally everything. So we list a bunch of third-party extensions as well. Other people publish PyPI modules, which have more strategies in them, or functions to infer strategies from whatever value or schema you might have. And those are listed in our documentation, though do note that, as is convention, listing them in our documentation means we know they exist, not we think they're great and we guarantee they're secure and awesome. All right, so we're going to go back into our breakout rooms and do some more of the exercises. We'll go through for, let's say, till 22, so 25 minutes for exercises, and finishing that up with another 10-minute break. So that's a chance to get up, stretch your legs, grab some coffee, and we'll aim to come back to this room for the third short talk at 10 to whatever hour it will be in your time zone. For me, 10 to 7 in the morning. Sun will be up. Thanks, Laura. All right, so that's the end of our scheduled break. Do we have everyone back with us? Thank you for everyone who thumbs up. I can see that you're back with us. I'm just not sure we've got everyone else as well. But it looks like 26 by my count. All right, let's jump into section 3. So just to recap, we had planned 4 parts of this tutorial. We've now been through the first part on basic property-based testing, and we've now gone through describing your data and done some exercises, and hopefully even taken a short break to stretch. I know down in Australia, I enjoyed that because the sun is currently rising. It's almost 7 a.m. All right, part 3 of our tutorial. We would probably call this like strategies or design patterns, except strategies is a taken word in Hypothesis and design patterns is also kind of a taken phrase. So I call these test tactics. And they're basically answering the question of, once you've got your decorator, once you know what information or data to pass into your test function, what do you actually write in the test? So that's this section. And that's basically the most common question that I get about Hypothesis. So there are a couple of common properties. And the reason I call these common is because almost every project will have multiple functions that these apply to for each of these properties. They range from what we call the fuzzing property, or just it doesn't crash when you give it input. In Python, that's like no exceptions or no unexpected exceptions. You have round trip properties, equivalent functions, and metamorphic properties, a scary word, which is actually a pretty cool thing to test. There's also situational properties, like just check whether the output seemed reasonable, like checking that a sorted list returns a thing that's in order. We also have the so-called algebraic properties that ended up naming property-based testing. And that's for things like if you have an addition operator, it's commutative and associative, that if you add 0, that's not an idempotent operation that doesn't change things. And I will briefly mention sort of stateful or model-based tests, just to explain that they're complicated and awesome and would be a whole nother tutorial on their own. And the last thing is I'm going to show off ghostwriting tests, which is a really neat trick, but we'll get to that. The thing to remember is that just calling your code is sort of somewhere between embarrassingly and terrifyingly good at finding bugs when you have hypotheses produce the inputs that you wouldn't think of. It's important to note this style of testing doesn't work so well if you have to write your own unit tests, because kind of by definition, at least for me, I never write a test with an input that I never could have thought of. I tend to only write the tests for the inputs that I did think of, and that means that when I wrote the code, I already thought of them, so the code works on the things I thought of. That's great. But if you're using hypothesis and it produces data that you're not thinking of in advance, just calling your code works shockingly well, especially if you assert the properties that you can assert in your code, not just in your tests. The second really general property that I think is relevant to almost everyone's code base is what I call round trips. And that's something like if I save my data and then I load it back in, I have the same data again. If I encode my data to send it over the network and I decode it, I have the same data back. If I send a thing between nodes and receive the thing, I have the same thing. If I convert from this data format to that data format and then convert back, I should have the same thing. If I multiply by A and then I divide by A, I should have the same number I started with. In that case, maybe unless A is 0. And so these round trips are typically critical to our code. They often have complicated inputs and outputs because particularly like the save load thing, almost everyone ends up persisting some state to disk or sending it between computers. And so that means that we're crossing all of these different abstraction layers in our stack, but it's also really, really critical that we get this correct for all cases. So property test your round trips. This is a great use case for the more complicated strategies that you've just learned how to build. Another common function, I mentioned equivalent functions, and we saw that way back at the beginning with our trusted sort routine. In your real code, this is more likely to be something like the answer doesn't change based on the number of threads that I run my function in, or the new version after I refactored it gets the same answer as the old version before I refactored it, or the old version from a different language, perhaps. You can also have cases where, for example, the order that you call functions in shouldn't change the end result. The final pattern here is that you can also have functions which aren't always equivalent, but are equivalent for a subset of inputs, or are equivalent in all cases except where certain known exceptions are raised. And so you can test that as well. Jumping into the sort of situational properties, what I call validating the output. I always feel really silly when I write these assertions. You know, the probability is between 0 and 1. The thing returned a string, not none. That the string was not empty, or it didn't have any null characters in it, which caused trouble. I do always feel silly writing these, and then they catch bugs, and I feel silly about not writing them more often. The best option, of course, is to put these assertions in your code if they're cheap to run. This basically gives you the fastest possible feedback for future changes because it's like a regression test where you don't even have to run your test suite. If you violate the property that you thought would always be true due to any later change, you'll immediately get a failure, and the failure will also be really local. Assertions in your code, I keep going on about this, but I love them because they mean that the error is raised right where the problem arises. You don't get the problem where like the data is polluted in some way, and then you find out a long, long line of function calls later, and it's really hard to work out where the bug happened. I mentioned sort of the commutative and associative properties. They're honestly pretty rare in Python code, but if you have them, you might as well test them. And if you look up the slides later, you can follow this link to see an example where some developers at Atlassian used these properties to actually think about how you would test an event stream implementation, where they were merging various event streams or backing them up or duplicating them. And they wanted to make sure that they didn't ever drop records or duplicate them and various other things. Model-based stateful testing gives you an API with hypothesis where instead of decorating a single test function, you write a class and decorate each of its methods. And then hypothesis will choose the order of method calls to make as well as the arguments to those methods. So basically it's choosing what action to take as well as what input to take that action with. This is super powerful. It's great for exploring APIs, including web APIs. But honestly, it would be a whole workshop. So we're not even going to do any exercises on this. I just wanted to tell you that it exists. The final really common property is what are called metamorphic relations. A metamorphic relation is any property that holds between executing your code twice on slightly different inputs. So these properties tend to be a little more complicated, but they also mean that you can talk about how things change in a known way or how certain known changes shouldn't cause any change in the result. So while they're more complicated, these properties are also quite general, and you can often find them for almost any system. So a couple of examples. This graph is from a paper titled Equivalence Modulo Inputs, which said, if you generate a program and then generate an input to that program and run the program on the input, you'll get some result. If you then take the same program and mess around with every part of it that wasn't covered by executing that specific input, you'll have a different program, but it should still calculate the same result for that input because we haven't changed any of the code which executed on that particular input. So you then recompile it and you discover thousands of compiler bugs. It's a pretty cool trick. On many things, you have the idea of scale invariance, that if you multiply all of your inputs by some constant factor, your output should have that same constant factor. Or perhaps if it's completely scale invariant, you should get the identical output, no matter how you scale up your inputs up or down. You might have, for a sorting function, this property that if we have a list of numbers and we negate them all, so flip the sign, and then sort them, we should get the same result as if we sort them, then reverse the sorted list, and then negate them. In date times, I helped test out AstroPy a while ago, which has all different time reference frames. And the test that we used there was if we add a little time delta and then change the time zone that we're dealing with, we should have the same end result as if we do those in the other order. This is, in fact, the equivalent function that I talked about earlier, but we're using two different inputs. So we have a kind of equivalent metamorphic function. And in a sort of financial example, we might want to have the property that our tax code ensures that if your income increases, that never makes your post-tax income decrease, because then why would people want to earn more? The two general categories of metamorphic tests here then are that if you add things which shouldn't cause any change, your function is equivalent or it gets the same output. Or that if you make a certain kind of known change, then you get a known change in the output. And often that will be like, if I move the input in this direction, then the output moves in the same direction too. But the really short summary of this, to be honest, add assertions, fuzz your code, write the round trips, and then like relax and go home. You'll be done. This will find probably 80% of the bugs that I tend to find with property-based testing. And for many projects, I'll just write a couple of round trip tests and then stick to unit testing for the rest if hypothesis doesn't seem to make sense. Since there are no questions in the chat, I'm going to move on to a live demo. Wish me luck. So the hypothesis ghostwriter is a relatively new feature of hypothesis, which grew out of turning up to similar conferences like PyCon and having people tell me that hypothesis seemed really cool, but they weren't quite sure how to use it or what properties to run it. And I thought to myself, well, you know, this seems like a case for automating things. So let's see how the the hypothesis ghostwriter works. We have a hypothesis command that you can run in your terminal now that you've installed hypothesis. And we've got two different subcommands here. If you were using an old version of hypothesis, the code mod command will help refactor your code to update to the newest version. But today we're interested in the write command to get tests written for us, which sounds pretty cool to me. So hypothesis write, as the name might suggest, writes your property tests for you. So let's try writing, if I can even spell hypothesis anymore, a test for the sorted built-in. So here we are. It imports given and strategies from hypothesis, as you've seen, and it identifies that there are 3 arguments to the sorted function. Thanks, Victor. We have an iterable, which can be an iterable of integers or an iterable of text. We have our key function. We didn't actually think to test that in our earlier sorting example. And in this case, the key function is none. So it'll just look at the elements directly rather than having a function. And reverse might be either true or false. So we could sort in either increasing or decreasing order. So that seems like a pretty useful test to me. We're going to call the sorted thing. We're not going to make any assertions, but if you just save this to your own test file, you can add those afterwards. We might also say we know that the sorting function is idempotent. That is, if we run the sorting function on a sorted output, it should stay sorted, right? Running sorted on its own output makes no further changes. And so if we tell hypothesis that it's idempotent, that's exactly what we get. We have the same given spec for all the inputs, but then the test body now goes, we calculate our result, we repeat that by sorting the result with the other same arguments, and then we assert that we have the same result the first and the second times. Make sense? Maybe I got up too early to be able to type. Oh, but the sun is rising. That's nice. So we could also ask hypothesis to write us a test that things are equivalent. And let's say we've got the eval built in. So this takes a string and evaluates it as Python code. But if you're thinking I should be a little security conscious, you'll probably use the ask.literal eval function, which works just like eval, but it won't run arbitrary code. It only evaluates things like string literals or set literals or numbers or tuples of those things or whatever else. So literal eval is great if you have a string representing a data structure and you want the actual data, but you don't want people to be able to wipe your hard drive. And so here's what we've got. This time, the ghostwriter has given us 4 arguments, globals, locals, a node or string, and source. And we get our result of evaluating the source code and our result of literal eval on, oh, hang on, we've got different arguments here. So we're going to have to edit this test a little bit. We're just going to delete probably the source argument, and we'll pass node or string as the first argument to eval here. We might also want to change the strategy from the text strategy to something that actually looks like valid strings for literal data types. But the ghostwriter has still given us a decent starting point for our tests, at least. All right, last example. Let's have hypothesis write us a somewhat more complicated one. I mentioned that you don't often see something like the addition operator in your own code, where you'll have this commutative and associative property. But if you do, the ghostwriter totally knows how to handle it. In this case, we've got 3 tests. We said there aren't actually type annotations here, so we don't know what the arguments to add should be. Maybe we'll say they're integers or floats. And then once we say that, it'll check that a plus b plus c is the same as a plus b plus c. Or that regardless of how we order them, a plus b equals b plus a. And this final one says, maybe there's an identity element that adding a to something else gives us a. And for addition, that's 0. So we just replace this string with 0, and we'll see that addition seems to work. Of course, if we've got floats, we'll then discover that not a number plus 0 does not equal not a number, because not a number doesn't equal itself. But that's life sometimes. especially if you're dealing with non-number. All right, back to our slides. That's the complete set of slides for our third part. So we're going to jump back over into our exercises and go through to Notebook 02 on test strategies and common test tactics. So it's currently 12 minutes past. Let's give ourselves 20 minutes and come back at 35 past the hour for our final very quick talk before we wrap up for the day.
Okay, and so I'm going to go ahead and pause the recording and place people into the breakout rooms, and we'll see you soon. I believe you're muted, Zach.
I am. Thanks very much, Laura. Would it really be a Zoom call without the speaker leaving themselves on mute at least once?
It really isn't. Yeah, it really isn't.
Of all the traditions to keep from 2020, I think that's my favorite one. You're on mute. So given the time, I'm thinking what we might do now is we'll do the last section of talk, but instead of jumping into the exercises, we'll do our final Q&A session. And then instead of going to breakout rooms, you're welcome to stick around on the call working on exercises or doing Q&A until we end up wrapping that up. And then we'll be in the lounge after that. So let me share my screen and we can jump into the last section. And so specifically, the last section of our talk today is on all of the little details that you need to put it into practice. So now you know how to write strategies and how to write property-based tests and choose properties. This last section is basically about, well, how do you do that as part of a real-world project and test suite? So we're going to cover some things like design patterns for your test suites, including when not to use property-based testing, and some tips about how to write custom strategies that are reusable among your team on your project. We'll talk about settings and settings profiles and how those work. We'll talk about the example database, which records previous failures, whether you want to share it and how to do so. Some stuff about updating hypothesis and getting support for that, and a quick overview of coverage-guided fuzzing, which is a cool topic for advanced use. Our final set of exercises is basically running through this stuff to get you familiar with it, and then if somehow turns out we ran short of time, we would have thrown you into some real-world bug hunting using hypothesis. But that's going to be an exercise for you as you go apply this on your own code. So the first thing in designing property-based test suites or test suites including property-based testing is to remember that hypothesis is only part of the plan. It's not magic and it's not a panacea. So depending on the project, on some projects, I've written literally one property-based test. So if you've used the black auto formatter, they have a single property-based test with hypothesis that says, given any valid source code, you can format it with black without errors, and reformatting it doesn't make any further changes. That's the only property-based test that they have, but it's sufficient for black. On other projects, I've been more like 90% property-based. If I'm doing some mathematical code, and I know Ryan's done a lot of stuff with MyGrad, which is very heavily hypothesis tested. The other part of this is, essentially a hypothesis test is like a unit test. You can put it in files or on methods of unit test classes, just like usually would. So the thing to share is more about configuration and about custom strategies for your project. Maybe you have particular objects that you want to create more often, and having sort of a private strategies module where you predefine those cases can give you a great sort of single source of truth for all the weird things that your code needs to handle. And that means that if you add support for a new weird thing or you discover one from a user bug report, you can update the strategy in one place and then all of your tests will start checking for errors related to that, which is a much nicer pattern than having to update all of your tests for every feature separately. And so we've seen the specific patterns for this before. You can have functions that return strategies, maybe using the composite decorator if you need to. You can just assign a strategy to a global variable where you define the complicated details and then you can just refer to that variable later. And if you've got custom types, you can use register type strategy. The next thing is, of course, everyone loves print debugging, or at least I love print debugging. But if you use a print statement in a hypothesis test, print function, sorry, you'll notice that it prints for every time the example is executed. So hypothesis has a note function, the definition of which is print, but don't print unless this is the last example. So if you just want to see a shorter bit of output instead of possibly several hundred lines of text, just use note instead of print. You could even, from hypothesis, import note as print if you want it to be evil. The event function is slightly different. You pass that similarly, a string, but then at the end of your test, it will summarize, hypothesis will summarize for you what proportion of inputs had that particular string. So instead of telling you what happened in your last test, this gives you a sense of what happened averaged over all of your tests. And that's shown in hypothesis statistics, which will print something that looks much like this. You just pass PyTest the -- hypothesis shows statistics argument, and you'll see that, for example, while generating new examples, we had this kind of runtime, and you can see how much of that time was spent generating data compared to actually running your code. We had 9 passing and 1 failing example in this one, and 40% of our strings were short and 60% were a little longer. When we were then shrinking that to find the minimal example, we shrunk pretty quickly, and then we stopped because the test was finished. We had our failing minimal example. All right, next tip. Sometimes you'll be dealing with code that uses a random number generator. And random number generators are great because they make your code random, and they're terrible because randomness makes your tests flaky. So this might come up if you're using other tools like Faker for random testing. Personally, I'm not a huge fan, but I'll admit I'm biased in favor of hypothesis here. Or if you have something like a scheduler with exponential backoff and jitter, or if you're running some kind of simulation. Often the best option is just we have a random strategy. So if you can pass an instance of the random class, you can just ask hypothesis to give you one of those. If, on the other hand, your randomness is something like the results depend on the timing of the operating system threads, hypothesis can't help with that much with that. Sorry, but you might just be best off running in a single thread for that test. If you can't pass an instance of random that you get from hypothesis, we have this random module strategy. And it'll basically tell hypothesis internally to seed all of the global random number generators that it knows about. And in particular, you can add new random number generators from other libraries to that list if you need to. If there's an open source library that we don't know about yet, please do just open an issue and we can see about adding a plugin to handle that automatically for everyone. All right, settings. This one's fun. Settings are how you control what hypothesis does. So for example, if you want hypothesis to check more examples, you can just increase the max example setting. If you're concerned that your timing is flaky, you might want to disable the deadline setting in CI, and so on. So the profiles is where you can define a number of different kinds of settings or settings profiles in your test setup file, and then activate one of those based on, for example, an environment variable or a PyTest command line argument. You can also use settings as a decorator on a particular test function if there's just one that you want to run in verbose mode or for more examples. So the settings that I use most often, we have the deadline setting, and this defaults to warning you if ever executing your test function takes more than 200 milliseconds. That only gives you 5 runs per second, so it'd be 20 seconds for a single test on default. And that often indicates some kind of performance problem. On the other hand, if you expect your test to run for a long time, it might make sense to increase the deadline or just to turn it off entirely. The most common problem there is maybe your CI is running in a virtual machine, which is subject to unpredictable performance pauses. In that case, I tend to use a profile that just disables the deadline when it's running on machines that have this flaky performance. And max examples is the other one. If you want your test to be faster, just turn down the number of examples that it tries. If you want deterministic tests, so that you try the same set of examples every time, one setting is derandomize. Derandomize basically just seeds the random number generator that we use internally. Or to reproduce the test, you can pass -- hypothesis seed on the command line. This blog post is excellent by Nelson Elhage, a friend of mine, where he explains kind of the difference in attitude between people who are testing because they want to see if their pull request broke anything that was previously working, compared to testing with the motivation of finding any bug in the software. In particular, if you're just looking for regressions, often you'll actually want to have a deterministic output, because while you'd like to know about new bugs, you'd rather not know about them right now and block the pull requests that you're working on. As hopefully you've seen, if you need to reproduce a failing example with hypothesis, we shouldn't be flaky. You can just rerun your test and the database will handle that for you. If you want to make sure that everyone else on the team also sees the same examples, you can use the @hypothesis_example decorator. You just pass it the arguments, so the values instead of the strategies, and hypothesis will start by trying those explicit examples before generating its own. If you're in CI and the things that you're generating don't have a wrapper that you can copy paste, you can use the reproduce failure decorator. And that'll be spat out based on the print blob setting, which defaults to true if we detect CI. This is kind of ugly and it's definitely a temporary thing. You wouldn't want to commit this to your repo, but it is guaranteed to work. And when you need it, I'm always very glad to have it. So speaking of the database, you might want to share this with the rest of your team so that if anyone's test run finds a failing example, everyone else, when they run the test, will pick it up automatically. Since the default database is just a bunch of files in the directory, you could just share that directly, but I would tend to recommend instead using our support for custom databases. We already ship one that uses Redis if you have a Redis server set up, but if you have any other kind of key value store, all you need to implement is fetch and set and delete, and that's it. All right, next topic is about guided testing. So you've probably noticed that just trying random things in hypothesis works pretty well at finding bugs, but adding feedback to a search process can often be really useful. So the hypothesis.target function takes whatever score is meant to be maximized, and then if you want to try multiple scores for different things, you can optionally have a label. And at that point, we'll try to maximize each of the things that you show us separately. The advantage of target is that the chance of finding a bug actually increases over time as hypothesis learns more about what kinds of inputs lead to good scores. A couple of places where we found this useful. You can try to target the difference between two things. For example, for functions which are almost equivalent, trying to get hypothesis to maximize the difference between the results will often end up working and increasing that difference. You can try to maximize the number of tasks in a queue or the number of steps taken by some API, which will tend to drive hypothesis towards trying more and more complicated things. If you want to search for performance problems, you can try maximizing the mean or the average runtime of a task. You might want to deal with the compression ratio. And the final one is in cases where filtering would be too intense, we've noticed that it can be helpful just to basically use target to tell hypothesis whether or not the input was valid. For example, you might want to say, I only ever raise this particular exception type, and that's okay. I don't want to reject any input that raises that exception, but if I don't raise the exception, use target to try to prioritize more things like that.
And I just want to give a 10-minute warning before the Zoom room ends.
All right, thanks, Laura. So if you have complicated code and you don't want to set up all the targets, coverage-guided fuzzing is basically the idea that you can target executing a line of code. And Atheros is a Google library, which is a wrapper around libfuzzer, a classic tool for C or other LLVM languages. And libfuzzer is designed to run a single function for hours or even days, rather than fractions of a second. It's fantastic for C extensions and native code because it can do coverage of your compiled machine code as well. And it integrates well with hypothesis. You can see the example code down the bottom here. This is a complete integration. You define whatever test you have with hypothesis, and then you just tell the Atheros setup that you want to fuzz this fuzz1 input callback, which is attached to the hypothesis attribute, which is attached to the function you decorated with given. I will also say that I'm building my own fuzzer specialized to hypothesis. And it's designed, rather than fuzzing an individual function, to fuzz your whole test suite simultaneously. So it's pure Python. It works well on Windows as well as Linux and OS X. It has native support for exploiting target and event, and it runs all of your tests at once. My view is that you would use Hyperfuzz if you wanted better integration with the testing workflow for a team on an ongoing basis. And it's got great database support. But when I say great database support, I mean it's got exactly the same database support that everything else has. So that's not a unique advantage. It's just an awesome thing. If you need support for Hypothesis, we do not promise free support because no one's paying us and we do have jobs, or in my case, a PhD thesis I'm meant to be working on. Stack Overflow is generally pretty helpful though on the Python hypothesis tag. And we do have a mailing list and an IRC channel that you can hang out in. On the other hand, if you have a support or a training budget, I hope that you will all agree that we do great training. Last thing of the talk, updating Hypothesis. Hypothesis is of course very well tested. So we run a system where every pull request to Hypothesis is automatically released as a new version. That means that Hypothesis can update several times per week, or even at the sprints, maybe several times per day. On that basis, update at whatever pace works for you. Hypothesis does take stability very seriously, but it's still a good idea to pin your dependencies. This is just general advice, really. But the key bit is we update frequently. You should update on whatever frequency works for your team. That brings us to the end of the fourth and final section. But because of the time, we've only got a few minutes left. I'm not going to go send you off to do the exercises for putting it into practice. Those are in the repos. So you've all got access to those. And if you want to ask questions or work through it in the lounge, totally up for that. But for the end of this session, I'm going to turn us over to Q&A. And thanks very much for coming.
So, Zach, it looks like we have an interesting question about the semantics of describing what we've been discussing as property-based testing versus properties versus traits.
That is an excellent question. So Bernard's just saying it makes people think of class properties in Python. Yeah, it does. This is basically just a terminology problem because property-based testing was invented for other languages, where people were thinking about properties as in things which are always true of your code or your system of logic. One thing we did manage to avoid is calling strategies generators, which is what everyone else calls them. And that would have been really confusing because Python generators are a totally different kind of thing, which also give you a sequence of values over time. So we try, but it's probably a bit late to rename the whole style of testing just for Python, sorry.
And that said, we still haven't been super happy with the name for strategies.
No. But nor could we think of anything better. So here we are.
And so if anyone's interested, the way that I got involved in this was actually I was taking on my first really major Python project, and I was working on it mainly by myself. And it was a math library, and I couldn't stand the thought of giving students buggy math library code. So I needed to make sure that I could test this really well, which I found an old Hypothesis PyCon talk, and that's how I got involved in it. And so it really was the sort of thing where Hypothesis wasn't actually a very advanced tool. It was the tool that got me testing code to begin with. So I think it can be intimidating at times, but actually it's quite user-friendly.
I know that as a developer, I spend a lot of time working on error messages. And in fact, we've had whole pull requests in the past where the whole point of the pull request is just to detect some kind of issue, like where someone's asked a question because they've been confused about what's going on. And we'll add an error message specifically if we can detect that, like, it looks like you have the same kind of misconception going on. Let me give you a long error message that explains what's going on and what you might want to try instead.
put another way, without hypothesis, I think it's pretty easy to work yourself into a corner of some bad practices of manually defining test cases that end up being flaky and very limited. And you feel confident that your code is well tested because you put in all of this sweat and hard work, but ultimately it's very narrow what's being tested is something to avoid. Yeah.
There was an example in Num. Sorry, go Laura.
The only question I had is whether there were implementations of hypothesis within things like data frames, pandas. I read the comment that it's ready for NumPy and moving into Dask. So I'm wondering if data frames was covered along the way.
Yep, we also have a pandas extra, hypothesis.extra.pandas.
Wonderful.
We don't have one specifically for Dask because it's pretty easy just to construct a data frame or an array and then just map the Dask equivalent onto that with the .map method.
And different data structures, I'm thinking if I were to do things like parsing JSON blobs or doing cross comparison, can I extend some of these testing to more complex data structures?
Absolutely.
Okay.
Yeah, so the different techniques like that composite strategy can empower you to write something where individually you're making simple descriptions of data, but then you're stitching them together to form a much more sophisticated data structure, like a JSON blob. And then there's also some really nice built-in support with builds that will take your class, maybe your class is annotated, and builds will infer how to generate primitive data to populate your more substantial class, right? So but yeah, you can generate really sophisticated data. I've actually used hypothesis to generate graph data, so like nodes and edges in specific ways where it's like you have to have 5 connected components and each connected component needs at least 10 nodes, right? So it starts to get very rich. Yeah.
I think we have time for one more question before Zoom kicks us out.
Last one, Bernat asked us about database-powered example sharing, specifically putting the hypothesis database in a version control system like Git. The short version is we've designed the file format that we're using. It's basically just byte strings with a hash as a name to be friendly and work well in Git. That said, we would usually not recommend it because the interpretation of the data can vary a little between hypothesis versions. And it's pretty easy to build up sort of a sufficient quantity of binary data in your Git repo that you just start to slow down when you're cloning things. That said, if you still want to do it, we have made sure that it'll work.